Here we look at the properties of two or more masses. Here's mass 1 and mass 2. And what do we know about those masses? Shh, please. Yes, there is a force between them, isn't it? It's one of the forces that act at a distance. Is that what you said, Paul? So it's one of those forces that act at a distance. I can draw these forces from the center of that body, that mass. I can draw a force with respect to the other mass. How long would I draw this force here from the center of the body? Yeah, it's the same, isn't it? It's the same length. Okay. Force, and we might say minus F there, but I've drawn it in the opposite direction, so we don't have to put the minus. I've drawn the arrow in the opposite direction. And the law is Newton came up with this. Isaac Newton. Newton said, every particle in the universe attracts I'll go down here, particle. Attracts every other particle with a force that is directly proportional to the product, yes. Product of the two masses. And I know you guys don't like comma and English teachers these days. It actually fits here. And inversely proportional to the every particle in the universe attracts every other particle with a force that is directly proportional to the product of the two masses and inversely proportional to the square of the distance between them, and that is this, Newton's law of universal gravitation. Newton's law of universal. Does anybody know it? You all know it, actually. Yes. And I've just said mathematically what that last paragraph says, or that last sentence says. Where G is this gravitational constant, which is equal to 6.67 by 10 to the minus 11. If you think I'm wrong, please tell me. Sometimes I am. Which is Newton meters squared. Hang on. Newton meters to the power of minus 2 kilograms squared. Is that right? Oh, sorry, other way around. And of course it is meters squared kilograms to the power of minus 2. Where do those units come from? How do we get those units from this formula here? Well, look here. We've got kilograms squared on the top line, mass times mass is kilograms squared. A distance on the bottom line squared, which is meters squared, meters to the power of -2. And on the other side, newtons. In order to get this value, this force in newtons, we need meters to be squared, this bottom line, and we need kilograms to be the power of -2. And that's where this gravitational constant comes from. You'll notice something about that number. What is something interesting about that number, do you think? It's very small. Gravitation is a very small force with respect to the other three forces that we know, the other three main forces. If these are the two masses, this might be the distance between them, or this is the distance between them, and we call that r. Sometimes people have said, oh well, this is over d squared, the distance between them squared. That's true also. Force, and we can call this mass m1 and this mass m2. And that essentially says that everything in this room, including the gas that makes up the air and the tables and your fellow peers, is attracted to everybody else and everything else in here. Of course, there's one overriding. There's something that we're all masses. We're all made up of these small particles that are masses, and that they're all attracted to each other. But there's some force that overrides all of them, and therefore we're not sort of floating around in the air above this earth and slowly bumping into each other and coalescing. Yeah, gravitational force, which is the same force that attracts us to each other. There's a really large mass that we're sitting on, and that you'll notice that the larger, if one of these masses is very large, then of course the force goes up a large amount. And the distance is, well, the distance isn't that far. And there's the classic question: what happens if you dig a hole to the other side of the Earth? So, yeah, okay. So imagine we did this. End up in China. So I don't know whether China's directly on the other side of the Earth from Adelaide. I don't think it is, in fact. But if we're always drawing the Earth with Australia here. Don't laugh at my Australia. Okay, and if we're all down here and this is the equator, and we dug a hole through. I don't know what might be around here. Some North America somewhere might be around on the other side if we dug straight through. Maybe somewhere in South America. I'm not very, yeah, or maybe we'll pop out in the middle of the Pacific somewhere. There's one thing that is for sure that somebody's done the calculation of, and that is the time that it takes. And don't quote me on this. I heard this on the program QI. It's an excellent program, and they're usually right. In fact, I've never heard any of their. But does anybody know how long it takes to fall through here? This is apparently this is fixed. This is fixed no matter where you dig this hole through. It takes about 42 minutes. Okay. Now, 42 minutes. And what would happen is you'd jump into the hole here and you'd fall towards where? Center of the earth. And what would you do in that? What would you continue to do as you fell towards the center of the earth? You'd accelerate. If there was a gas inside there, you'd start burning up, wouldn't you? Because the speed would be so high, and the speed that you would reach would be so great. Problem is that as you're falling through here, of course, there's quite a bit of mass on this side of you as well. Imagine you jumped in here and you got to about there. Of course, there's quite a lot of mass there, and so that starts to pull you in this direction as well. And what happens is, yeah, theoretically at the center here, well, you wouldn't stop. You'd accelerate. Your acceleration would be in this direction as you went past center, but you would accelerate negatively. And theoretically, if there were no air, you could jump in here and jump out the other side at exactly the same speed as which you jumped in. Okay? That would be some mean feat. Of course, you'd have to hold your breath for 42 minutes, and you'd have to be in a pressure suit because there couldn't be air in that hole for that to happen. If we had the technology to do this, then Qantas would go out of business very quickly. Yeah, that's right. Exactly. Yeah, something would happen to the Earth. Yeah, these wouldn't. Of course, we know something about the center of the Earth, don't we? And we only know this by seismic waves. We measure earthquakes through the Earth, and we see that there's different densities as you go through. In fact, we've only ever drilled. Does anybody know how deep we've only ever drilled? They did. Russians did it. Yes. The Americans tried it. And they actually tried it in an ocean because under the ocean the crust is very thin. So you can imagine if they're sitting on a boat. They tried this in the 60s, I think it was. Don't quote me on that date. Here's their boat, okay. And what they did was, of course, here's the ocean floor. That's quite deep, and they drilled down through the ocean floor. The crust is very thin here, and when I say very thin, it's only 6 kilometers thick or something like that. And they tried to drill down. They didn't get very far. They got bugger all. And somebody likened it to trying to drill a hole in the pavement from the top of the Empire State Building with a piece of spaghetti. Okay, because this distance was so large here, and what would happen is the boat would be moving around, and they just couldn't do it very well. The Russians did it several years later. They actually drilled about 13 kilometers deep, which is about, I can't draw it to scale. It's not even that far. Okay, so we don't know what's inside there. The Russians never got through the crust. They didn't get down to the molten part. Certainly, if they got to the molten part, then the drill bit would fall apart anyway. And because the way these things work is they add pieces to the drill, and the drill gets deeper and deeper and deeper, and they pump water down, and the water gets flushed out. Of course, as you get deeper and deeper, the temperature gets hotter and hotter, and the water just turns to steam and that sort of thing. So it just doesn't work. We know by seismic waves what's going on inside the Earth, and we think that there's a molten core, and that there's areas of kind of plastic rock. When I say plastic, meaning they have some viscosity, and we just don't really know for sure. We haven't reached down and touched this stuff here. We're guessing at what's going on inside here. Pretty sure, but just guessing. So not only would you need oxygen supply and a spacesuit, a pressure suit, because you'd have to remove all the air out of here. You'd need some heat protection, because of course there's areas of molten through here, molten rock, and that hole's not going to maintain its integrity for very long at all. Back to gravitation and satellites. So Newton's law of gravitation. This works for two masses of equal size, and then we have this situation here, and I'm not trying to say this is to scale. This is the moon. I'll leave that Earth as it is. What do we know about the Earth and the moon and the forces? If I draw this arrow here, we'll draw it a little bit fatter. So the Earth pulls the moon, doesn't it? With a force. What does the moon's force look like? in the opposite direction is true. Smaller is not. I'm going to draw it like that because that's going to be easy. And while I've got this one, I'll draw this one too. Okay. They attract each other with equal and opposite force. Everybody's inclined to say it's a smaller force. It is not. Equal and opposite in all cases. Why then when I jump off of the Earth, this is not to scale. When I jump, why is it then that that I jump and I get pulled back to the Earth? If the forces are equal, because the forces are equal for me and the Earth also. Here's the force of the Earth on me and me of the Earth on the Earth. Equal and opposite forces, but when I jump, I get pulled back to the Earth. What's going on there? Oh, I'm only interested in me and the Earth at the moment. There's what? No gravity exerting a force on you? Did you say? I jump. I jump in the air, and I go back to the Earth, don't I? The Earth doesn't appear to go anywhere. Why? Why, if these two forces here are the same? Why, if this force, of the Earth on me and me on the Earth are the same? Why is it that the Earth doesn't? We don't meet each other in the centre. And imagine if we all jumped at the same time and that happened. Because the masses are different. Yes. Because the masses are different. Let's have a look at this. Yeah, I don't know. Okay. I've drawn a better picture. This one's still not to scale. I better say it. Not to scale. Now, and I don't know what length we would draw these vectors, but I'm being pulled towards the center of the Earth, and the Earth itself, and we always draw these forces from the center of the masses. The Earth itself is being pulled towards me with equal and opposite force, and I'm being pulled by all of the Earth. In fact, like there's mass through here as well, and they've done tests where they've looked at the masses of mountains. So mountains, of course, this is not to scale either, but if you stand next to a mountain, then there's lots of Earth next to you there, and so you kind of pulled that way a little bit, and they can measure that. Okay, that's measurable. Now, if I jump, the Earth doesn't come up to me. I go back down to the Earth. Have a look at Newton's second law. Newton's second law says what? Force equals mass times acceleration, doesn't it? They are vectors, aren't they? And so we might say, okay, we'll look at the mass here. We'll call it big M and me little m. What happens when I put given the same force? Yeah, what happens? Yeah, same force, isn't it? That's really important. People forget that even though I've said it. Same force. F, here it is, F equals F, but opposite direction. So we'll say F equals minus F. Same force. If I change the mass to F equals M A and F equals M A. Okay. Can you see what happens? So same force, exactly the same force. If the mass is large, the acceleration is very small. If the mass is small, the acceleration is very large to maintain this constant F. To maintain, it does. It does. It moves up towards me. When I jump, it moves up towards me. And there's, they did a test. I think it was 50,000 people jumped all at once. Have you heard of this one? Yeah, they coordinated 50,000 people to all jump at once, and it was immeasurable. It wasn't enough mass. They measured seismic waves because of their jump, and so the thunder of them coming down was measured by a seismograph. Yes, but they couldn't measure the movement, the acceleration of the Earth. And vice versa. I won't write the next sentence. That's why I appear to move a whole lot. You guys appear to move a whole lot, and the Earth doesn't appear to move at all. It moves. It does move a very small amount, but not very much. Or accelerates a very small amount, and hence changes its velocity, and hence moves some distance, d, but a very small amount. Gravitation is always attractive. I better make a statement about the equal and opposite force. Quiet now, please. Gravitation is mutual between two masses. If body A exerts a force on body B, Body A exerts a force on body B, then body B exerts an equal and opposite force on body A. I've just spent a little bit of time saying that, but I better write that down. One of the other comments is I wasn't complete with my notes, so I'll try and be as complete with my notes as I can be. Let's see, do I want to say that here? I don't know whether I'll fit that in here. Let's get a new one. The force is proportional to the mass, whether that be mass 1 or mass 2. And what that says is, if the mass of one body doubles, then so does the force. And so on and so forth. I'm not going to write as much as they did in the textbook. The law of gravitation is an inverse square law. This says that the force between two bodies is in inverse proportion to the distance between them. Inversely proportional to the distance. F is proportional to, that little insignia said means in proportional to. Is in proportion to 1 on r squared. So what happens if I double the radius? The force. Yes, that's right. If the radius is doubled, If it's tripled, it's divided by 9, and so on and so forth. This is interesting. Some people will get this straight away mathematically. If the distance, or actually I'll say radius to keep with what I said before, radius is multiplied by 3/4. That is, it's only 75% of the radius before. The force is, does anybody know what it is? Okay. If you think about that, if I put R becomes, so let's have a look at that. R becomes 3/4 R, 75% of R. Then I can say this: F equals 1 on 3/4 R squared. All right, which is the same as 4 on 3. Let's bring it to the top line. Squared. R squared. Okay. Just leave the R squared out. So you'll have to do some calculations with that later, and there'll be some examples. How much time do we have? 10. Try this example. This one isn't so hard, is it? What do we write first? We always write our, start with your formula. Show the examiner or me, makes it easier for me to mark as well, which formula you think you're going to use. Even if it's incorrect and you're just trying it out, write it in there. Use your scrap paper if you're in a test. Never forget, this is a classic problem that students face, that little squared. Everybody have a go at calculating it. Who has calculated it? 3.5? 5? 10 to the power of 22 newtons, yes, is the units. And yes, that's fine. That's a good answer. Notice also we talked about significant figures and decimal places used in the tests and the exams. You tend to write the answer with the least amount of significant figures given in your in the values that you're given. And in this case, it was 3 decimal places, so we would stick to that, even though it's, yeah. So what was, did you get better? That's right, nice. Okay, so go with the least accurate. Accurate is double C. Accurate of the decimal places of the values equals 3.546 by 10 to the power of 22 newtons. Did anybody have any difficulties with that question? Easy, good.